All right, so this is moment of inertia example number 1. Use integration to determine the moment of inertia of the rectangle about the x-axis. So one thing we should be careful about is that with this, I'm trying to be careful with respect to whether the axis is a little x-axis or a big x-axis. So we're going to work through this problem again in a minute, and we're going to look at a different axis. It's going to be the capital X-axis instead of the little x-axis, so that's important. Let's see, I want to make sure I get this, or I want to try and get this problem right the first time, which is kind of odd for me. I know you're not used to that, but all right, so let's see, if we go to the next slide. There we go. I made some grid paper up. I'm going to try and do some inking right here on this slide here. All right, so we're looking for the moment of inertia I sub x, where we want to know the moment of inertia I about this little x-axis. So what I'm going to do is take I sub x as little x-axis there is equal to the integral over the area of y squared times dA. So that's the fundamental equation, and if you look at our equation sheets, I won't bring it up on the screen right now, but our equation sheets do have that on there, so you don't have to memorize that. You can just take that as a given to start off with. So what I need to do, if I'm looking for the moment of inertia about the x-axis, I need to sketch a differential area, and it's going to be a strip that is parallel to the axis that I'm looking for. So I'm looking at a strip like that, and this is going to be the differential area dA. So that's going to have a height like this. We'll call that differential height dy, right over top of that axis there. And it has the width b. You can see that at the bottom. So we can write that dA is equal to b times dy. All right, now the distance y is going to be the distance from that axis measured to the center of our differential area. So that is the distance y, like that. So what I can do then is come back up to my equation, and I can rewrite that, do some substitution. I have I little x is equal to the integral of, let's see, y squared times dA, but I know that dA is now equal to b times dy. And if I'm integrating over the area, then I need to go from basically from the bottom of this section here all the way up to the top. So I'm integrating from minus h over 2 to a positive h over 2. So those are the bounds of my integral. So here I write minus h over 2. Here I write positive h over 2. I wish I had a finer point marker, but I don't. Okay, so we can do the integration here. I sub x is equal to, let's see, b comes out in front. I end up with the integral of y squared, which becomes y cubed over 3. And then that's evaluated from our bounds of minus h over 2 to a positive h over 2. So if we expand that, then what we end up with is b times the quantity. Let's see, that's going to be h over 2 cubed is going to be, let's see, let's bring this out there like that. So that's going to be h cubed over 8. And then that's going to be a minus h cubed over 8. And so we end up with, as our last step, well, let's do the algebra because I screw that up a lot. So this is going to be b over 3. This is going to be 2h cubed over 8, or h cubed over 4. So we end up with our final answer that I sub little x is equal to bh cubed over 12. Okay, that's a big deal. We're going to use that a lot. It's written down for you on your equation sheet, but you'll probably memorize that after you do the homework problems. You probably won't forget that again. So if we wanted to, we could go in here and look at a different axis. So let me see, I'll go ahead and write this. If this was the y-axis here going through the centroid, then we could write that I sub y is, instead of being equal to b times h cubed over 12, is going to be b cubed times h divided by 12. So we basically just spin that block around, look at it from the other direction, and you get a similar result. Use integration to determine the moment of inertia of the rectangle about its base, about the big x-axis. So let me go to the next slide where I have grid paper. So we'll start off and solve this the same way. Instead of writing I sub little x, now I write I big X equal to the integral over the area of y squared times dA. And I need a differential area, and so I'll take that here. It's parallel to the x-axis. It's parallel to the axis that I'm interested in. So this distance here is dy, and this distance here now is my distance y, like that. And if I'm integrating over the area, then what I do is I integrate from the bottom of the section down here at y equals 0 to the top of the section up here at y equals h. So, one more step, sorry. The area of this differential area dA is equal to its width. The width here is constant regardless of where we're at, regardless of the value of y. The width is equal to b, and then the thickness is dy. So then I can do some substitution. This is equal to the integral over the area, so it's the integral from 0 to h of y squared times dA, which is b times dy. So in this case, then we end up with b times, let's see, it's going to be y cubed over 3 when we integrate evaluated from 0 to h. So we plug that in and we get that I sub big X for this is equal to bh cubed divided by 3.